Good morning. Questions about anything before we dive in? Let's get going. So today we begin chapter 5. We finished up chapter 3 and then had our test on it. And then Monday we had a couple of loose ends from chapter 3 that we needed to talk about to tie a ribbon around that. So we did that. And so we don't do chapter 4 in this class. So we'll skip over that and we're now in chapter 5. And chapter 5 is on program optimization. And the techniques that you learn to use in order to make your programs run fast or efficiently on the computer. So the idea is that given knowledge of the architecture of the computer and how the computer actually operates, how do we write programs that exploit the capabilities of the computer in an efficient way versus what would you do in a program that would not run quite so fast on the computer. And so we'll look at a bunch of these sort of standard optimization techniques, some of which the compiler will do for you, some of which you have to kind of do for yourself. So the overview of what we'll be discussing is originally we'll look at some types of coding optimizations that are pretty much applicable to whatever language you're programming in. They're just general sort of things that you do when you program that are more efficient than some other way of expressing the same thing. So we'll look at those kind of things, and then we'll look at things that you can do that make it hard for the compiler to help you out and optimize things. And eventually, we'll have to learn a lot more about what's going on in the actual CPU with the pipeline and all this kind of stuff to learn how to exploit instruction level parallelism, which is a really important thing if you really want your program to run as fast as possible. So let's get going. The concept being expressed here in this slide is that when you take a course in analysis of algorithms, 301, 305, 405, those kind of classes, they're going to teach you about what's referred to as the big O notation, order of complexity of an algorithm. And so you'll be learning things like, this particular algorithm, if you feed it n inputs, goes through n squared operations to compute the result, or maybe it goes through n times log n operations, or maybe it's order n. So that'll be assigning to each algorithm a asymptotic complexity for the overall algorithm. And study things like, bubble sort is an n squared algorithm, and quick sort is an n log n algorithm. So as n gets bigger and bigger and bigger, those two things get further and further apart. N squared grows much bigger than n log n, right? So in all things being equal, I would prefer the n log n algorithm unless there were some other properties that I wanted that it didn't have. So that's the kind of thing you'll learn in those analysis of algorithms classes. And the other thing you'll be doing in those classes is, if it worked out that the actual formula for the complexity of the algorithm was something like n 5n squared plus 27n plus some constant, in those analyses, you'd say, oh, well, the order of the algorithm is n squared, and you just ignore all the constants and you ignore all those lesser terms. But in reality, when you go to implement the thing on the computer, those things actually make a big difference. It's not just that, every n squared algorithm is equal or something, right? There's ones that have a lot of big nasty constants in front of the thing and then other terms in there that are less than n squared. So the point that's trying to be made here is, well, those analyses of the complexity of the algorithm is a good thing, and in general, one would prefer, an algorithm that was a lesser order of complexity. But when you go to implement it on the computer, there's a lot of other considerations other than just the complexity of the algorithm that are going to determine how fast the thing actually runs on a real computer when you implement it in code. And it's not uncommon that a naive implementation of an algorithm versus one that's tweaked with some of these optimizations we're going to look at would run many orders of magnitude slower, 10, 20, 30, 40, 50, maybe 100 times slower than one that was coded understanding the architecture of the computer and how to take advantage of the way the computer actually works. So that's what we're doing here. So in other words, a novice programmer would implement something and, maybe it would take 30 seconds to compute the result you're after. But understanding how the computer actually works, maybe there's a way we could implement the same thing and make it take 2 seconds or 1 second, right? So nobody wants to wait on the computer. You want to write things that execute fast. And that's part of becoming a real programmer, right? Not a beginner. So we have to understand how the programs are compiled and executed on the actual computer. And we have to do tests to measure the actual performance that we're getting when we implement things this way versus some other way. So we want to learn how to do that. So compilers are very good these days at doing a bunch of optimizations for you. And we've seen many examples to this point of this kind of thing going on. One of the biggest optimizations that compilers do is in the allocation of registers. As we've seen, putting something in memory or taking something out of memory is a very expensive operation in terms of the number of cycles it takes, number of clock pulses it takes on the computer versus doing operations on things that are in registers, right? So the compilers go to great lengths to try to figure out what to keep in the registers and um, how to avoid spilling things back to memory as much as possible. And so there's a lot of optimizations that go on in these compilers in terms of figuring out how to allocate things to the registers. And in general, they use a algorithm in the compiler called a graph coloring algorithm to do the register allocation scheme that you learn about if you take the compilers classes, how those things work. But that's a really important optimization because touching memory is expensive. We've also seen examples already of code selection and code ordering. Remember the example where we wrote some computations down in C and then we looked at the assembly language and it was computing the same result, but the sequence of the operations was completely different from what we had written down in C because it figured out it could do it more efficiently if it did it in a different order. So code ordering and the actual codes that are selected by the compiler is another big area of optimization. Another kind of optimization compilers would do is sometimes there'll be stuff in your code that never gets executed. So a space optimization would be just to throw that out, not generate any code for it. We've seen another kind of optimization that's related to this dead code concept when we were writing little examples and we saw that it had optimized away an entire function call because the compiler figured out, well, you called this function and you messed around with some stuff, but you never did anything with anything you computed in that function outside of that function. So there's no point in even calling it. So we just threw the whole function call away, right? So dead code and elimination is another kind of optimization compilers do. So usually, but not always, strangely enough, when you apply some optimizations to the code, you don't actually change the order of complexity. An n squared algorithm is still going to be n squared, although that's not completely 100% true, strangely enough, and we'll see a couple of examples of how that works out. It's also really the case that when you implement an algorithm, if you make some errors, that you don't do certain kinds of optimizations, you can actually increase the order of complexity in what you've got implemented versus what the actual algorithm is. And we'll see today an example of that. So it can go both ways, but usually it's the case you're not going to make it any less than you started out, although strangely enough, there are some examples where that could actually happen. So that being the case, the order of complexity is kind of the dominating factor, I guess, right? But the point being made here is that, okay, that's great, but when you go to implement it on the computer, you can have something that runs 50 times slower if you don't pay attention to how you're implementing it on the computer, right? So then we'll look at some things that prevent the compiler from doing certain kind of optimizations and how to possibly avoid some of those. The optimizing compiler is ultimately constrained in the sense that whatever it does can't change the result that's computed, right? As we saw in the one where it reordered the code, it reordered the sequence in which the computations were being done, but it computed the exact same result. So if it's the case that by doing some particular optimization, it would work for 99% of the cases, the compiler can't do that optimization. It has to work for every single case, right? So it's constrained in that sense by what it can try to do to optimize things. Other things that the compiler might not be able to optimize would be things that might be obvious to a human, but not so obvious to the compiler. And we'll see examples of that here today in the later slides. Another thing you have to realize is that when compilers do these optimizations for you, that by and large, mostly, not completely, totally, but to a large extent, all the optimizations that they do are sort of myopic. They're just looking at one procedure or one function and optimizing the code within that little box, right? They're not in general able to do optimizations where you kind of pull the focus out and look at a larger chunk of the code in the program and do what we would call inter procedural type optimizations. There are a few instances where it can do certain things, but in general, all of the optimizations that go on are pretty much intra procedural. They happen within the box of the code for one particular function, right? So that being the case, uh, embedding a call to a function kind of like makes it drop everything it was doing and start some other from scratch type of optimizations within that function that you're looking at. So we'll see that in a second too. And the other thing is the compilers can only look at the static information that's known at compile time, right? I mean, so if there's some variable that you're reading the contents of in at execution time from the user for providing input, the compiler can't take advantage in any way of the range of values that actually ended up being input to the program. It can only use information that it knew statically at compile time and not the nature of anything that occurs dynamically. So the general rule is when the compiler can't guarantee that doing something to try to optimize something would compute the exact same result in every single case, or it can't know whether it would or not, it can't do the optimization. So it's constrained by those types of parameters. So let's look at our first one. These are what we call generally useful optimizations because they sort of apply to every programming language you're ever going to write in. They're not specific to C code, and they're just sort of general, basic, fundamental things that all programmers should learn to do things a little more efficiently than maybe some novice might do. So the first one we look at is a instance of a general class of optimizations we call code motion optimizations. And the effect of the optimization is going to be to move a computation from one place to another, so code motion. So the example we have here is a little simple loop. You have a pointer to a double and a pointer to a double and then two longs. And the intent here is we're going to use this A thing. You're going to pass in a two-dimensional array. We have the pointer to the beginning of the array. And we're going to go compute our own subscript, treating A like it was a one-dimensional array. You've seen this before. We're just going to take the number of columns in and we're going to multiply that times the row index and add the column index to get to the right position in the thing, treating it like a one-dimensional array, right? So rolling your own subscripts. And we're going to walk across the array varying j, which means we're going to walk down a column of that two-dimensional array, and then we're going to put the values out of that column into a vector B, right, of j elements. So go get me the column j out of this two-dimensional array and put it in this guy. And that's what this thing does, right? So we look at the code and we see this n times I, where we're taking the number of columns in that's passed in here, and we're multiplying it by the row index. And we're doing that inside the loop, but nothing about n or I depend in any way on j or anything else that's computed inside this loop. So that's what we call a loop invariant. N and I change not at all at any point in this loop. So why compute n times I inside the loop? Why not put it up here, compute it one time, stuff it in this variable, and then just use that variable over and over again? So it doesn't really matter what language you're programming in or what computer you're compiling this for. This always would make sense. Why do all these multiplications when you only need to do it once? Why do it n times, right, as you went through the loop? So this is an example of a code motion optimization because we're moving the code from inside the loop, moving the loop invariant outside the loop. Does everybody understand? So some beginning programmer might write this thing down on the left, but anybody that's programmed, for any time at all would go, well, that's silly. I don't want to do that. I want to put this outside the loop and do it one time. So you say, well, okay, you saved yourself n minus one multiplications. Well, a multiplication instruction on this computer maybe takes 3 cycles. So depending on how big n is, it's 3n cycles. You say 3n minus 1 cycles. So what's the big deal? Well, maybe that one instance doesn't save you a whole lot of time. This doesn't run massively faster than that. But in general, if you keep doing this over and over again, then your programs are going to start running slower than they could by not applying these kind of optimizations. And there's really no point in wasting these cycles when you could do it this way and compute the same thing, right? So we look at code, and so this code basically, if you read it, is just going to do what you expect it to do, where we um, take the thing and put it outside of the loop. And now this one, what it's doing is it's going through the loop from j equals 0, j less than n, right? And it's taking the row pointer thing that we've computed as a, the beginning address of the array, plus ni, right, to get to the row that we're uh, concerned with, right? To compute that ni value one time. And then we just keep incrementing across the thing, right, to get to the next position, right? The next column position. So the next type of optimization we do, and compilers are really good at noticing this one and doing it for you, but you can also just make sure it happens by doing it yourself. You've already seen this. It's called a reduction in strength. So we can simulate multiplying by 16 by shifting left 4 bits. It takes one cycle to do this shift operation, one pulse of the clock. It takes 3 cycles to do that multiply, right? Pumping the thing through the multiply circuitry. Of course, the downside of doing the shift is that it doesn't light up the condition code bits necessarily, that you would have if you did the true multiply. So you have to watch out for that kind of thing. It might happen, but in general, you can get by with it. So depending upon the cost of the divide or multiply, they're saying on an Intel NALM, they have these code names for these different implementations of the Intel architecture, and we'll look at different ones as we go through the course. But this is a Core i7, original Core i7 type of processor architecture, the NALM. And so they're saying on that it's 3 cycles. Other computers, maybe more or less, who knows. So another reduction in strength that we could do, and this one the compiler might not be able to see and figure out for us. It probably wouldn't. You would have to do this as the human looking at this and going, oh, I can see how I can do this cheaper by substituting a cheaper operation for the one that's in there. We got a nested for loop varying I and j across some 2-dimensional array, computing up the subscript into the 2-dimensional array as if it was a 1-dimensional array. Take the number of elements times the row index, add it to j, put it in the vector for the column vector. Same thing we had before. So now we're going to do that now for every row, right? That's why we have the nested for loops, slightly different from the previous one, right? So for every row for set I, I'm going to go in and then I'm going to get this stuff and put it in the B sub j, right? So if you look at that, you're doing the multiplication inside the inner for loop. But since you're walking across columns, right, you're varying the column index, right, for a fixed I for the inner loop, right? then rather than doing that multiplication, if you wanted to walk across the column, you could do it like this, right? You could compute the ni as 0 to start with. And now in the inner loop, I'm going to vary j from 0 to n minus 1, right? So what am I going to do? I'm going to pick up the 0th with 0 for the row index, right? I'm going to pick up all the columns in that 0th row and put it into this b sub j thing, right? So then I increment ni by n, right? So which takes me what? The length of a row, right? Rather than doing the multiply by the I index, I can increment it. And I get the same thing as 0 times n, 1 times n, 2 times n, 3 times n, right? But I get it by doing addition. 0 times n, if I add in there, I get 1 times, I get the 2 times, I get the 3 times, the 4 times, right? Just by doing addition rather than multiplication. So this is a reduction in strength over the multiply, but the compiler probably isn't going to figure out that it could take this thing and rewrite it for me by generating a temporary variable and then starting it at 0 and then doing addition rather than doing the multiplication inside the inner loop, right? So that's a reduction in strength that the compiler probably wouldn't do for you. Another type of optimization that compilers do a lot of, but sometimes they can see them and sometimes you can see ones they can't, is a thing called redundant common subexpression elimination, or in general, doing something with a common subexpression. A lot of times, if you look up a formula in a math book or an engineering book or whatever, you'll notice that the sort of natural way of expressing the formula may have the same term in there like 3 or 4 different times. You know, it may have x squared plus y squared, which expresses some concept, right, in the formula 3 different places. Well, that may be the sort of natural way of thinking about it, expressing it in a mathematical way, but that isn't the way you would implement it on the computer. You certainly wouldn't want to keep computing x squared plus y squared 3 times if it's the same thing over and over again. So that's, if you feed that kind of a formula to the compilers are smart enough to recognize these sub-expressions that are redundant, right? And compute it one time and just keep using the result. So they're pretty good. They're pretty smart at that redundant common sub-expression elimination. But the one in the example here is a way of computing the same thing, noticing that the problem has a sub-expression in a sense by virtue of an algebraic transformation. And the compilers aren't any good at doing this kind of thing, right? In general, the stuff that you just take for granted in your head about looking at something and looking at the algebraic equivalences and things like that, the compilers aren't anywhere near as good at that as you are, right? So if we look at this code, we have this thing where we have a two-dimensional array once again, and we're going into the two-dimensional array val, and we're rolling our own subscripts, right? Treating it like it was a one-dimensional array and having a point ij in the array, and we want to get all the neighbors of that point. So think of a matrix, two-dimensional array, and there's a point in the matrix, and you want to look at all the neighbors that live right next to it. And you want to, in this case, sum them up is what they're doing. So what would the subscripts be for those guys, treating it like it was a one-dimensional array? Well, point ij If I took I minus 1 times n, the number of things in the column, it's a square matrix, this example, and then you add j to it, then who are you referencing there? You're referencing the same column, but at the previous row, right? Similarly, this one, I plus 1 times n plus j, is the ij guy's neighbor to the south. The first one is his neighbor to the north, and I plus 1 is his neighbor to the south, the row below him. And then the next one here is the same row, but the column on the left, that's his western neighbor, right? And then this one is the same row, and the neighbor to the right within that row, that's his eastern neighbor, right? So we call these the news neighbors, north, east, west, south. So you're thinking of a point sitting in that two-dimensional array, and you're accessing all the points that sit right next to it. In the row above it, the same column, the row below it, same column, in the same row, the column before it, in the same row, the column after it. Those 4 points are the news neighbors, and they're summing up the values of those news neighbors for the ijth point, the neighbors of point ij. Well, you say, well, that's kind of strange. Why in the world would anybody want to do that? Well, it turns out that there's an awful lot of algorithms that do this exact kind of thing. I don't know if you guys have had differential equations yet, or you haven't gotten to that, or maybe you have. But one way of getting numerical approximate solutions to some differential equations is to use techniques that we call finite difference methods. And finite difference methods, if you implement them, and in particular Jacobi iteration and finite difference methods to solve those equations, you end up with a hunk of code that looks a lot like this, only what in general you're doing is you're getting the average of all of the 4 neighbors, and you're generating the ijth point for the next iteration of some sequence of things by averaging the points around the point to produce the new value for that point in the next version. So we do these kind of computations endlessly on the computer. It's not just an arbitrary pedantic example. And if we look at that, and we looked at this code for the way it's written there, we got 3 multiplies, 3 adds going on, right? And then we actually have another add and a subtract going on because we're using the load effective address trick, right, to do it for us. So in reality, we've got five simple integer operations. That's what we call the plus and minus, and 3 complex integer or expensive integer actual real multiplies, right? But we look at the code on the right and we say, well, shoot, I can compute a variable called I times n plus j, right? I want to get those 4 points. So this would be the offset from the beginning of the array where the ijth element in the array lived, right? That would be how far from the beginning of the array he was. Well, how far from the beginning of the array is his north neighbor? He's in elements, right, back from where ij lives in the array. His south neighbor is in elements past where ij lives, right? The length of a row, the number of elements in a column in this case. Where is his west neighbor? Well, he's just 1 element to the left, go back 1, and then go 1 to the right. That's where his east neighbor is. So if I computed this I times n plus j thing, I guess you use it 4 times, doing 4 simple arithmetic operations, plus and minus, right? And that gives me those values at those locations, and then I just sum them up, right? So I didn't do but one multiply. So I look at the code, I got one multiply. I don't have three multiplies anymore. And now I have a handful of adds and subtracts, right? So this is obviously going to run a lot faster than the stuff on the left. And this is a common sub-expression that's been pulled out. But this one, the compiler would never see because this is kind of an algebraic thing, right? Noticing that, oh, well, embedded into all that computation you're doing there, you're just going a certain distance from the location where the ijth element lives in the thing, treating it as a one-dimensional array. Go up a column, go down, go up a row, go down a row, go to the left in the column, go to the right in the column in that same row, right? But noticing this is inherent in that computation is not something the compiler was going to see. So this is the kind of stuff that a beginning programmer might write it like the one on the left, but anybody that's been programming for any amount of time is going to go, well, I don't need to do all those multiplies. I can just do this one multiply and then just do some additions off of that and compute the exact same stuff, right? Which is another reason why we might take a two-dimensional array and treat it like a one-dimensional array, right? Because if you subscripted this thing with subscripts like it was a two-dimensional array, you'd be generating an awful lot of computations to get to those locations, right? We've seen the formulas that are used. So it'd be much more efficient to just do this, which is why we might in C do these things of treating a two-dimensional array like a one-dimensional array, right? Does everybody see that? So these are the kind of optimizations that you have to learn how to do to write programs that execute fast. The next one, it shows you a optimization blocker, right? In general, not completely 100% true, but in general, compilers do most all of their optimizations inside a single procedure, right? And when you see a procedure call, the compiler isn't going to do any optimizations across the boundaries of those procedure calls. So in general, procedure calls are kind of like a blocker to any further optimization. It has to kind of stop all the optimizations, start over from scratch within that other procedure, right? They're not going to do any optimizations that span across the two procedures. So this kind of is an example of that. It's a really egregious example of that. We have this little function here that's going to take a character string, a pointer to a character string, right? The string and sees a bunch of characters sitting in memory with a null terminator at the end of it. We're going to walk across the string. We're going to look at all the characters. And if they're uppercase letters, we're going to turn them into the corresponding lowercase letter. So we have this thing here that iterates across a for loop for all the elements of the string, s sub I, going from 0 while I is less than the length of the string, keep incrementing the thing and just walk across it. For each one, what do we do? If s sub I is greater than or equal to the character uppercase A and s sub I is less than or equal to the uppercase Z, then I'm looking at a uppercase letter. So it's going to replace the s sub I with the difference here. Well, what the heck is that? Well, let's look at an ASCII code chart. If you've never looked at one before, here they are. These are the codes that we put in a byte to represent these characters, right? So we put the code hex 41 in to represent the character A. To represent the character lowercase a, we put a hex 61. And notice how they line up, and they're all 20 hex away from each other. So the chart, the code table for the ASCII characters isn't just some random arbitrary thing. It's organized in a certain way, right? Get the numbers, they all appear in sequence here, starting at hex 31 or 30 for 0, right? So the code that we had over there before is saying take the code for the character A, which is hex 41, and subtract the code for the little a, hex 61, and you're going to get the distance in that table between the upper and the lower case things, only it's a negative number, right? So when you subtract the negative number, you're actually adding. So it's going to add hex 20 to this thing. It's kind of screwy. I probably wouldn't have written it like that. I probably would have said little a minus big A, and then I would have done a plus, which kind of makes more sense to me. You're adding 20 into the thing, but whatever, either way, it works, right? So in any way, we're turning the uppercase encoding for the uppercase letter into the encoding for the lowercase letter. But that's not why we're looking at it. We're looking at it because of this silly string length thing sitting here in the loop. What does string length do? Well, how does string length work? It's a library function, presumably, right? How would it get this length of a string? Well, in C, what do strings look like? They're a bunch of characters followed by a null, and the only way you know the length of it is you walk across all the characters, adding them up, 1, 2, 3, 4, 5, and then you hit the null and you stop adding, right? So that takes order n if there are n characters in the string, right? So when we run this little program here, and we look at how long it takes as you vary the size of the string, we notice something weird. We get something that looks quadratic, right? But our for loop should just be order n. So what's going on? Well, if you looked at some go-to-ish version of of a string length implementation, you check to see if the I was greater than the length of the string, you'd jump around the loop. Otherwise, you go into the loop, and then you'd be doing this at the bottom of the loop. So the point they're driving home is you're doing this call to this function n times, right? For the length of the string being n. But the length of the string doesn't change inside the loop, right? So why don't you just get they're saying this is kind of like what string length would be. You're just assuming it's implemented something like this, set length equal to 0, and then walk across the thing looking for the null character and keep increment to the right, increment the length, and then when you bang into the null, you return the length. So it's an order n algorithm to give you what the length of the string is. So now we have this order n algorithm being called every time we call string length. So that's kind of silly. Why don't we just call string length once, put it in this length variable, and then use that in the loop? So we're not calling the string length function n times. We're just calling it one time. So that obviously would run a lot faster. And then you ask yourself, well, shoot, why can't the dumb compiler do that optimization for me? We've already seen some code motion optimizations that it might know how to do. Why can't it move that out like it moved that n times I thing out of the other loop? It's the same kind of thing, code motion. And the answer is, well, it can't do that optimization. And the reason it can't do that optimization is it has no idea whether in calling the string length function, whether the string length function has some sort of side effect, right? Suppose, just some bizarre example, suppose we wrote the string length function so that it walked across the string and added up, however many characters there were, but also reached up into some global variable and incremented the number of times the string length function had been called or something. In other words, it modified the referencing environment outside of the function. That's a side effect, right? The compiler doesn't have a clue whether string length has a side effect or not. And if it has a side effect, then you need to call it n times to get those side effects to happen n times, right? So it wouldn't be the same thing being computed as if you only called it one time, right? So that is showing you that the compiler kind of treats the procedures as a black box and is not doing these inter procedural optimizations. And this is kind of an example of that, that it can't do that code motion trick, moving the call to the function out and just doing it one time like it did with the I times n multiply thing, because it doesn't know whether or not the function has a side effect or not. Now, there are certain programming languages that are designed in certain ways that we can tell whether the function has a side effect or not, but C is certainly not one of them. C is kind of the wild, wild west, and we're monkeying around directly with pointers to memory and doing arithmetic on them and all kind of crazy stuff, right? So the nature of the way C is designed, we'll see that we kind of get bitten for all this flexibility of grabbing the computer by the throat and monkeying around with addresses and all that kind of low level stuff. We kind of pay a price for that because there's certain kind of optimizations that in less loosey goosey kind of languages you could do that you can't do in C. And we'll see examples of that. This one is an example of the fact that the compiler just assumes that every function might have a side effect, doesn't know, doesn't care to look. I mean, you presumably could write a compiler that could go over and look at the code for the string length function and try to figure out whether it had a side effect, but that's not as easy as it might sound, right? Because what if that function in turn calls some other function, which in turn calls some other function? Now you got to chase down this sequence of calls of 4 million things that might get called, looking to see if any of them have side effects, which means that the first one you started looking at effectively has a side effect. So they're going, well, how many days do you want this thing to take to compile? We're not going to run around through all these things and try to figure out whether these things have side effects or not. So they don't do that, right? That would be kind of an inter-procedural style optimization that they don't do. There may be some weird compilers for some certain types of languages. I can think of a language like Euclid where they would actually do that sort of thing to try to outlaw side effects from functions. But in general, that isn't going to happen. And it's certainly not going to happen in a C compiler. They're not going to go traipsing around through all these bazillions of call chains trying to figure out whether a side effect happened to do this code motion optimization. So the compiler doesn't do that, which means you need to do it. You never would write as a real programmer, right? Something that looked like that. You'd get this length of the string one time before you hit the loop, and then you'd use it, right, to compare to see whether you wanted to be in the loop or not. You wouldn't embed a function call in there that is an invariant, right? I times n as an invariant is bad enough, but an actual function call, you've seen all the overhead associated with making a call, all that stuff that goes on to set up the parameters and go over there and then mess with the stack maybe and move things back and forth and return things. And so all that overhead associated with implementing a function call, you don't want to pay for that over and over and over again, right? When you don't have to pay for it but one time. So that's another kind of code motion optimization, but one that you would have to do. And so effectively, if you do it the dumb way, right, putting the call of the string length in there, you've taken what ought to be an order in algorithm and implemented it in such a way that you've now turned it into an order n squared algorithm. It runs like an order n squared algorithm rather than a straight line, right, on the bottom there, like it ought to run, right? The speed that it takes ought to just be flat and increase with n, basically, right? And not look like this quadratic thing. So we will learn more and more of these optimization techniques as we go on. Tomorrow we will learn about one called loop unrolling, and that's the one that you need to solve the two homework problems. So we need to get that one uh, covered tomorrow. So you have a couple of days to get that implemented. Office hours on Wednesdays are at 1 o'clock, remember? So I'll be there from 1 to 2. So we only have two balls juggled in the air this week. You have your project and your homework due Friday, right? And then Monday, you get a new project and a new set of homework. Yeah, it's just that there's nothing in there for homework 6 yet. I gotta put something in there. So yeah, it does contribute to the grade. So I'll have to go in and modify that. All the homeworks sum up to that, whatever it is, 18 points, or for us, it'll probably end up being 16. So 2 points per homework, basically. Anything else? Okay. Well, good luck on your defusing your bombs, and read ahead in the chapter to try to understand what loop unrolling is, and we'll talk about it some tomorrow. But you need to know that to do the homework for this week. So I'll either see you at 1 or I'll see you tomorrow. Have a great day.